see. Data tools. Uh, let's see if it's streaming. Okay, Twitch is live. And let's see YouTube. Okay, YouTube's also there. Last where we left off, we finally fixed this bug that was happening with the lighting. So yeah, this was a very annoying bug to fix, but it is done. Now we shall continue with the series. We'll be doing uniform buffers today. It's fairly short, so I might try and do the next tutorial as well, which is the descriptor sets. We'll see how it goes. Okay, let's get into it.
Come up against some of the limitations of push constants, namely the limited space. For more complicated shaders, we would like to be able to provide more data. To do so, we will use a uniform buffer. A uniform buffer is a way to provide arbitrary read-only data to our shaders, just like we've done so far with push constants. However, uniform buffers can be much larger. The minimum size specified by Vulkan is 16 kilobytes. Some mobile devices will use this limit. Desktop-based devices will more commonly have 64 kilobytes available. But uniform buffers are not strictly better than push constants though. Reading from uniform buffer memory can be slightly slower, they require additional setup on our end, and require binding before a draw call is made, which can also introduce additional overhead. If you recall, we actually already have some experience working with Vulkan buffer objects. When sending a model's attribute data, we use a vertex buffer to store the per vertex information. A VK buffer is the same object type used for uniform data as well, with the only difference being the buffer usage flag. So before we create a buffer with uniform data, I think now is a good time to create an abstraction for Vulkan buffer objects. I've gone ahead and done this, and have put a pastebin link to the code in the description below.
Yeah. Let's create the header file and CPP file. There will be a buffer and over here as well. I'll be buffer. Yeah. Let's close all this old code. Delete and delete.
Into your project and rename the class.
Paste one. Let's copy it. Yeah, let's see. Yeah, let's copy this. Yeah. Let's get the implementation. Okay. Hmm. Okay, let's just clean things up a bit. Mhm. Yeah. There we go. Let's save everything. Let's close these.
Class and namespace to match your project conventions. I'm not going to go through all of this code line by line because it's pretty self-explanatory. It simply wraps a VK buffer and VK buffer memory into a single object. It provides functions to apply common operations to buffers, such as mapping memory, writing to the device memory from the host, and
Get buffer, get map memory, get instance counts, get instance size, get alignment size, get usage flags, get memory property flags, get buffer size.
so on. I've also included index variants for each operation. These are useful for grouping multiple instances into a single buffer, rather than using a buffer per instance. Finally, we have some getter functions for the private member variables. One thing, though, that's a bit less self-explanatory is the min-offset alignment field. Similar to how fields within a push constant or uniform object need to follow certain padding guidelines, instances of a uniform block must be at an offset that is an integer multiple of the min uniform buffer offset alignment device value. For this reason, I've included a helper function that takes an instance size.
Right.
One thing, though, that's a bit less self-explanatory is the min-offset alignment field. Similar to how fields within a push constant or
Yeah, a lot of these are just like one-liners. Hmm.
need to follow certain padding guidelines, instances of a uniform block must be at an offset that is an integer multiple of the min uniform buffer offset alignment device value. For this reason, I've included a helper function that takes an instance size and the min offset alignment and returns the smallest size in bytes that satisfies this requirement. Okay, that might have all been a bit confusing. So for example, if an instance of a uniform buffer object is 19 bytes, and the minimum offset alignment for uniforms is 16 bytes for your device, then to pack multiple uniforms into a single buffer object, we need to have an additional 13 bytes of padding. So in that case, the instance size will be 19 bytes, and the alignment size will be 32 bytes, the smallest integer multiple of 16 that fits an instance. Vertex and index buffers do not have an alignment requirement, so we can use the default value of 1, but for objects like storage and uniform buffers, this is required to be properly set. Okay, now before creating a uniform buffer, let's refactor the model class to use this new abstraction. In the model,
Let's go to the model class. Hash include the buffer.
change from using separate buffer and device memory handles to instead using a unique pointer of type LVE buffer.
Std unique pointer LV buffer vertex buffer.
Similarly, I'll also update the buffer and device handles for the index buffer.
Index buffer.
The E buffer. Then in the model implementation file, start by removing the contents of the destructor. We no longer need to manually destroy the because the LVE buffer class will now handle cleaning up buffer resources automatically for us.
Yeah.
Handle cleaning up buffer resources.
Yeah. Yeah.
Create vertex and index buffer functions to instead initialize an LVE buffer instance. The buffer constructor is pretty similar to the create buffer function, except instead of taking the buffer size directly, it takes separate instance count and instance size arguments. The buffer size is then calculated within the buffer class by first calculating the alignment size and then using the alignment size times the instance count. I'm going to create a new variable of type UN32 called vertex size equal to the size of vertices.
Whereas here done this. Yeah. U and 42T. Vertex is
Unable to be accessed from the CPU. So we use a staging buffer as a temporary location to copy data on the CPU to the GPU and then transfer the data.
only buffer staging only device vertexes vertex count. Yeah.
Optimal device local memory. So create an LVE buffer staging buffer, initialize with the device.
That vertex is that is 0.
Vertex count, and then the same buffer usage flags and memory property flags as used below. And then you can remove the prior declaration for the staging buffer.
I can delete all of this.
Okay, so the LVE buffer class has functionality to make mapping memory and writing to the buffer a bit
Staging buffer.map. Staging buffer dot write to buffer.
We can map the entire buffer memory region by calling staging buffer.map. Then we write our vertex data to
Void start vertices data.
data. But make sure to first cast vertices.data to a void pointer. This replaces the functionality of the 4 lines below, so we can now remove them. We staging buffer.unmap, since that will be handled automatically when the staging buffer is cleaned up. Now we can initialize the vertex buffer, which is a unique pointer, so set vertex buffer is equal to std make unique LVE buffer with the device, vertex size, vertex count, and the same usage and memory flags as used below. So vertex buffer bit or transfer.
Yeah, unmap is not needed. What is this C++ style? Hi Rahul, thanks for joining the stream. How's your day going? C style. Fast versus C++ style. Let's see what the difference is. Custom. Oh, yes, static cost. Asking the compiler to do whatever it can to make the cost. We'll just stick with what is in the tutorial for now.
For destination bit as the usage flags, and device local bit for the memory property flags.
Where were we? Yeah. Vertex, buffer, STD, make unique, only buffer. Add one exclamation at the end. Now we reverse vertex as vertex count. Then these two. Currently, this is just to both like to learn Vulkan and also to refresh my C++ skills because I haven't used it in a long time. But after this, I plan to continue my previous series of of learning the Unity UI toolkit. So Unity has like a new way of handling UI in games. So I was previously working on that, testing things out. And yeah, after the series ends, I plan to continue with that for a bit. Uh, and once uh, the learning Unity UI was to make a better template for any future games that I want to make. Because in future games, like you're always going to have a menu. So it's nice to just have like one reusable system. So I'll also be testing out some new plugins and things. So if you're familiar with Unity.2m, this is a pretty popular animation package library type of thing. And it just makes animating a lot easier. Recently, I found out, at least when I started that previous series, that there is a open source version called Prime Twin that essentially does the same thing, but is more performant and uses like less memory. Yeah, it's an allocation-free animation library. So that's one of the things. I have a bunch of other plugins that I might want to test out as well. So yeah, that will be my goal after this whole Vulkan thing is done. I might try and add some of my own functionality just to learn some more about Vulkan. Uh, but yeah, after that I'll go back to Unity. Maybe I'll do some multiplayer stuff, but I'd rather focus on getting a solid template for any future games that I want to make. The Vulkan thing is mostly just to like learn things, because having knowledge about how game engines work will always be helpful if you're in the like game development scene. So yeah, and also like C++ is also helpful to know. Oh yeah, I haven't touched it since 12th grade. So, and even then, like you would just do everything in one CPP file. You wouldn't really have that many header files. So this is just like a new experience. Yeah. What about you, Rahul? What are you doing these days? Are you doing any like project? Are you like working? Yeah. Let me continue with this before I forget where I left off.
To transfer from the staging buffer to the vertex buffer.
Yeah, this can be deleted. Staging buffer dot get buffer. Um, not get buffer.
The last two lines cleaning up the staging buffer. The staging buffer is a stack variable, so it will be automatically cleaned up.
Yeah.
Buffer function ends. Okay, now we pretty much have to do this exact same thing for the create index buffers function. Just below the buffer size initialization, initialize
You and 32T index as of indices and staging paste index size and index count. Host visible, property host coherent, usage alphabet. Let's see.
then create a staging buffer, call .map, and write indices.data to the buffer.
Maybe buffer. Yeah, there we go. Staging buffer. I'm on the website of thing working as a full stack dev. Always wanted to learn game dev, making my own engine. It's fascinating. Uh, yeah, I would not recommend starting with Vulkan, but definitely give it a try. Also, just as a tip, use the CLI editor. 1 second. Yeah, use the CLI editor. I initially started with Visual Studio Community, but that was such a headache to use. And this one was like just so much easier to find bugs and all. With VS Code, there's no like, you can technically get it working, but it's a much bigger headache even compared to uh, the VS community. So definitely, if you're doing C++ type of things, use CLI. It's so much better. Uh, yeah. Also, if you're not familiar with C++, definitely like watch some tutorials on that, because this stuff is generally more advanced topics. So I had done it in 11th and 12th, so I was already familiar with most things. And even if you're already familiar with coding, it should be fine. But yeah, at least go through some like refresher courses or something. And if you're deciding to do Vulkan, definitely check out this tutorial. This has been pretty good so far. All the other tutorials are much older, so they're like much more outdated. And some of them require to have made a previous engine, and they're not going to like teach you from scratch. So yeah, if you're trying to check it out, definitely check out this one by Brendan Gallia. I'll share the link. Let's see. Share, copy, and we post it in the chat. Seems to have been sent. Okay, let's continue with this. Where did we leave off? Okay, create vertex buffers. We did that. Now add the index buffers. Control C. Paste. Void indices data.
Initialize index buffer with a make unique function.
Then let's copy this. Copy an extra bracket. There we go. See index size and index count. Search index buffer bit and transfer it. Property device local. Okay. Copy, paste. Usage transfer, memory property local bit. Okay. Map and map. Yeah, these two can be deleted. And this can be index buffer. Yeah, let's delete all of that.
From above, make sure you have the correct buffer usage and memory property flags. And then finally update the copy buffer function arguments and remove the last two lines cleaning up the staging buffer. The only remaining thing to do is fix the bind model function. We need to provide the underlying Vulkan buffer handles.
Yeah. Dot get buffer and index buffer dot get buffer. There we go.
So this becomes vertex buffer arrow get buffer and index buffer arrow get buffer. And that's it. Now's a good time to test your code to make sure everything is working the same as before. If I build and run, I can see my two vase objects. Move the camera.
Yeah, let's save and test this out. Hopefully everything runs properly. Okay. It crashed. Let's try it again. Crash again. What is happening? Let's minimize this. Yeah, let me check. It's 19. we change the model CPP. Okay, here it's supposed to be index buffer. Yeah, let's try it again. Some building. Yes. Yeah. And this is the one with flat shading. And this is the one with the smooth shape. Yeah, nice. Okay, glad I found that quickly. I didn't want to have to spend another hour trying to figure that out.
Around and resize the window with no issue. Okay, now that we've got that bit of refactoring out of the way, let's create a uniform buffer. We'll do this in the app implementation file. First include the LV buffer header, then just within
Okay, first app first CPP.
struct called global.
Let's make the screen bigger.
Okay, now that we've got that bit of refactoring out of the way, let's create a uniform buffer. We'll do this in the app implementation file. First include the LV buffer header.
Let's make this bigger so that you all can read it as well.
Then just within my namespace, I'll declare a struct called global UBO.
Right. This is in first app CPP. Okay, similar way I started it. Okay, Ash include away model. No, is the buffer. Buffer away. Small.
Implementation file. First include the LV buffer header, then just within my namespace, I'll declare a struct called global UBO with fields glm map 4.
Okay, another struct global UBO. How's it going on? Yeah.
Initialize to the identity matrix. And a glm
Injection
vec3 field
wheel.
called light direction. And initialize that to glm normalized glm vec3 of 1, -3, and -1. This struct is going to serve a similar.
Yeah, let's say projection glm mat 4 injection wheel. By the way, if you are going to like get into making a game engine, be prepared for a lot of vector maths. But like it's mostly there during the initial setup. Now after that, it's been fine. Vec3 light direction. Equals glm normalize. First, let's make this 1.0f. And we have the lighting data somewhere. There's the transforms. Where did we put the light position? Now we'll just enter the values. glm vec3 1 minus 3.0 f and 1.0
The
f
purpose is
again.
a simple push constant data struct.
It's minus 1.0. Yeah.
Pass in read-only data to the pipeline shaders. Now at the start of the run function, let's create a uniform buffer. The arguments are the device, the instance,
as you're doing it at the start of run, alv buffer global UPO buffer.
and instance count, and the buffer usage and memory flags. I use an instance count equal to the max frames in flight, which is the value that dictates how many frames can be submitted for rendering simultaneously. This way, we can safely write to frames UBO instance without having to worry about the possible synchronization issues.
Okay, let's add in these properties. Let's say alv device, comma, and size of global UPO, then alv swaption, max frames in flight, VK buffer usage, uniform buffer bit, then VK memory property post visible bit. Okay. And next is LV device dot properties dot limits dot min uniform buffer offset alignment. Yeah, saved.
For example, frame 0 could write to a UBO 0, record its command buffer, and submit for rendering. And then frame 1 can write to a UBO 1 even if frame 0 is still rendering and reading from UBO 0. So by having 2 copies of the UBO, we never need to introduce extra waiting or synchronization. Double buffering like this should be
Right. What
rendering.
was he
And then frame
saying?
1 can write to UBO 1 even if frame 0 is still rendering and reading from UBO 0. So by having 2 copies of the UBO, we never need to introduce extra waiting or synchronization. Double buffering like this should be used whenever you have a dynamic resource that is written to each frame. Next, since this is
Okay. Yeah, this is kind of just rendering 2 frames in parallel almost. Maybe asynchronous might be a better word.
the uniform buffer that will contain multiple instances, we need to specify the min offset alignment. We can find this value in the device.properties.limit struct. Finally, note that we are not using the device coherent memory flag. This is because we want to selectively flash parts of the buffer in order to not interfere with a previous frame that may still be rendering. Okay, now moving on, now that we have successfully created a buffer, we need to call map on the buffer to name.
Yeah. Yeah, the end of a global map.
Writing to its memory. Next, each frame we need to update the buffer's data. So just below, in the if block where we begin a frame, we're going to have 2 distinct phases. The first phase,
Let's see. Render update.
and memory, followed by a second phase where draw calls will be recorded. I declare a local frame index variable for convenience, and then declare a global UBO instance and set the projection view field to camera.projection times camera.getView. Next, I will write this global UBO data to my buffer object using the right
Yes, let's start end frame index. Frame index alv dot get frame. Right. Get frame index. Frame index is never used, cannot resolve symbol dot. What? End frame index. Did I mess something up? Symbol? Dot get current frame index. U global UView. Camera dot get projection view. star camera.get view. Then let's see, global data buffer, global UBO frame index.
where the index is the frame index. Finally, because we did not use the host coherent memory flag, I now need to manually flush the memory.
Let's keep the names the same. Shift F6. UBO. And frame index, then we're flushing the buffer. Not flush. Yeah.
If you build and run, things should work just as before.
Oh, just doing flush index. Flush index. Frame index. Yeah, let's save all of this.
I haven't actually changed anything. Each frame we update the uniform buffer, but that data is actually never used within our shaders yet. We need to tell the pipeline object where this buffer is and how the data within it is structured. To do so, Vulkan uses descriptor sets, an additional layer of abstraction. This is what will be covered.
Right.
Anything. Each frame we update the uniform buffer, but that data is actually never used within our shaders yet. We need to tell the pipeline object where this buffer is and how the data within it is structured. To do so, Vulkan uses descriptor sets, an additional layer of abstraction. This is what will be covered in next week's tutorial. Before ending this video, I'd like to do one more thing. Currently, if we want something like render systems to have access to external information, we pass in each field individually. This can make things pretty tedious if
Okay, let's hit play first and fix any errors. Hopefully there's nothing. And run properly. Okay. It's all running fine. Got lost for a second though. Yeah, everything seems to be rendering correctly.
we ever want to change
Now
what data
let's
is
go
provided.
back here.
We would have to update the function signatures and every single function call. So let's create a new header file called LVE frame info containing
Okay, creating a new file. So header file new LV frame info. Let's delete all this. Pragma fonts. Include
frame info struct. This will wrap all frame relevant data into a single object, which then can easily be provided to any system's function calls. For now, all we have is
okay, let's see. LV camera and libraries include Vulkan / Vulkan.h. Then namespace LV struct frame info.
for in-camera state. In the future, we will be adding more onto this.
Okay, let's see. And frame index float frame time vk command buffer LV camera. Ampersand and then yeah.
Then, in the simple render system header, include the frame info header and update the render game objects function to now just take two arguments, a reference
Okay, simple render HVPP. Okay, hash include. We frame info HPPP.
To the frame info and the vector of game objects. The render game objects function to now just take two arguments, a reference to the frame info and the vector of game objects.
Okay, this can be deleted. Then frame info command buffer. Info and command buffer.
Next, in the render
Frame info.
systems implementation file, let's update the function signature to match.
I have to delete the bracket. Cannot resolve frame info.
Sure, we will be adding more onto this.
We make a class out of this and
Then, in the simple render system header, include the frame info header and update the render game objects function to now just take two arguments, a reference to the frame info and the vector of game objects. Next, in the render systems implementation file, let's update the function signature to match, and then change.
Okay, let's copy this. And the implementation file. And game objects. Yeah, paste.
The four occurrences of command buffer to use frame info.command buffer, and the two occurrences of camera to be frame info.camera.
Frame info. Info dot get command buffer. And projection view. Frame info dot get projection. Frame info dot get view.
Okay, cool. So the last thing to do is prepare the
Frame info dot camera dot camera.
each frame. So at the start of the begin frame if block in our app implementation, add frame info, initialize with the frame index, the frame time, command buffer, and camera.
Here was this in the first app, CPP. Load game objects. Yeah. Global update frame info. Yeah. Frame info. Frame info. Info. Brackets frame index. Frame time.
Finally, update the render game objects function call with the new arguments, build and run, and everything.
Okay. Command buffer and camera. Frame info. Okay, that's fixed. That's fixed. Will we render game objects?
The same as before. Sorry for not the most exciting tutorial today. Uniforms and descriptors.
Let's go back. Simple
The render
render
game objects function
CPP.
to now just take two arguments: a reference to the frame info and a frame info struct. This will wrap all frame relevant data into a single object, which then can easily be provided to any systems function calls. In the future, a reference to the frame info and the vector of game objects.
Frame info and then game objects. Yeah.
Next, in the render systems implementation file, let's update the function signature to match, and then change the 4 occurrences of command buffer to use frame info.command buffer, and the 2 occurrences of camera to be frame info.
Frame info and command buffer. Yeah. Paste and paste. And go. Let's put these all on separate lines. Yeah. Set enter and enter and push. Yeah.
Info.camera. Okay, cool. So the last thing to do is prepare the frame info.
Frame info dot camera get projection. Net frame.
So at the start of the begin frame if block in our app implementation, add frame info, initialize with the frame index, the frame time, command buffer, and camera. Finally, update the render game objects function call with the new arguments, build and run, and everything should be the same as before. Sorry for not the most exciting tutorial today. Uniforms and descriptor sets just require a bit of initial setup before becoming useful. Anyway, thanks.
Let's test it and see if everything still works. First tab on
Hope you're looking for with the new arguments, build and run, and everything the same as before. Sorry.
okay. Game objects, frame info. Save. Any other errors? Let's play and see. Okay. Movements all working, lighting is all working.
For not the most exciting tutorial today, uniforms and descriptor sets just require a bit of initial setup before becoming useful. Anyway,
Now let's check the comments. Overlook the non-coherent atom size value. Memory ranges that are flushed must be an integer value multiple of the device limit in size and offset. Hmm. Intuitive as to why the code is used in a particular way. Thus rush around the topic like giving a speech. You have to wait more than 2 weeks for your video to come out. Gotten some alpha feedback. I should explain why. And last time just saying exactly what I'm typing out. To cover textures, render passes, and frame buffers. First, as I think, without having the context, it's difficult to fully understand the swap chain code. Alternatively, as I mentioned, Vulkan tutorial. Nothing I can really do about this. Yeah.
Thanks for watching. Hope you're looking forward to the next tutorial and keep on coding.
I know this one
So
is
there's
a
an issue
bug fix. Oh, let's get into
with my
this.
implementation from last week's tutorial, and that's when flushing a single index, I didn't take the device limit non-coherent atom size into account. The non-coherent atom size is basically the smallest memory range your device allows when syncing between the host and device memory. This means that when we call flush index, you may have gotten an error because the memory range of a single instance didn't align with the non-coherent atom size. I'm actually not really sure why this didn't cause a problem on any of my machines, since the previous min offset alignment I was using of 32 bytes should have caused an issue. But perhaps my graphics driver was doing something behind the scenes to hide this. As a band-aid fix, we could include numeric and then calculate the
And for steps, CPP.
as the lowest common multiple of the min uniform buffer offset alignment and the non-coherent atom size. However, I don't really like this implementation. I was trying to be fancy by combining the uniform data from separate frames into a single buffer object, but in hindsight, I think this only makes things confusing and harder to follow. It can also cause potential problems such as the one here, where flushing the desired memory range becomes difficult. So for now, let's split this into two separate buffers. I'm going to undo what I just added, and instead create a vector of pointers to our buffer objects. We will use a buffer object for each frame.
Where's this? Just above the global. STD vector. STD unique pointer. LV buffer. UBO buffers. Yeah.
To initialize the vector of pointers, we need to loop over each index and call make unique. And then our arguments for creating the buffer are pretty
Wait, this was done in the run function. Here we go. Always swap chain max frames in flat. For and all 0. I equals 0. I less than UBO buffer size. Then I plus plus.
except for now, we only use an instance count of 1 per buffer.
Okay, let's see. UBO buffers I equal STD make unique, movie buffer, okay, and copy this. Control S, delete this.
We could also now add the coherent memory
Maybe option, but let's replace with 1.
to worry about manually flushing the memory. But I'm going to choose to leave that out for now.
We can memory host coherent bit.
Demonstrate the flush function. And then still within the for loop, we need to call the map function on each buffer instance. Next, let's update the two usages. We won't be using
Okay, you go buffers map. Map.
since each uniform data will be stored in a different frame. To get the correct buffer for each frame, we use the frame index, and then we can call the write to buffer and flush functions.
What's the you go buffers frame index. Frame index dot write to buffer ampersand UO. Then UO buffers flush.
And that's really it for the changes. Build and run, and if you were getting those previous messages, they should now be gone. The previous method I first showed
client ID, use range. Okay, let's see. UO buffer. Okay, cool.
is also fine, so long as you fix the alignment issues. Feel free to use whatever method you prefer. Both are correct, but with the former method, it's up to you to set the proper alignment and flush the correct memory ranges. Also note, this change doesn't mean we won't ever be using the index buffer functions. They'll still be useful for when we have multiple instances of data per frame. So we'd still use a buffer per frame in that case, and each buffer would have a copy per instance. Anyway, thank you for watching, and sorry about this small mistake. Keep on coding, cheers.
And let's play and see how it goes. Okay, it's loaded up. It's all working fine. Finding a bug like this must, like, trying to find what the solution is must be so tricky. Which, yeah, next is
Last
the
time, we created a
descriptor
uniform buffer
set.
and updated its.
Let's save all of these changes first. Okay, finish 19 and uniform buffers. Commit and push. Let's update the stream title. Descriptor sets. Descriptor sets. Yeah, it should be updating now. Let's see if YouTube has updated the title. Yes, it has. Before we continue, let's play some chess. I'm feeling a bit sleepy. Hmm. Let's bring the bishop out. Let's unblock this. Let's take that. And just attack the queen. Let's get that. Let's take this. Can bring the queen. Let's protect the bishop. Can't capture, it'll be mate. Let's move here. Hmm. Let's castle. Let's now bring this here. Let's capture this. Get that. Queen. Get the rook. Check. Yeah, nice. Surprising how much playing a game of chess like wakes you up. Okay, let's go back. This can be closed. This can be closed.
Data each frame. However, we are not
Let's put this on full screen.
actually making use of it within our shaders yet, and this is because you can't directly bind a uniform buffer to be used by a pipeline object. Vulkan has an additional abstraction known as descriptor sets. Descriptor sets can be pretty confusing at first, since there are a few things going on at once. Descriptor, we are not actually making use of it within our shaders yet, and this is because you can't directly bind a uniform buffer to be used by a pipeline object.
Oh, let's play one more game. Hmm. Let's go here. Back the queen. Let's bring this out. So capture and capture. Let's capture you. Uh, let's just capture equivalent pieces. Hmm. Let's go here. Let's castle, coincide. Bring this here. Capture. Capture. Bring this here. Check. Get rid of this. Capture. build up the pawn structure. Okay, so let's move back here. Yeah, and just bring this out all the way. Get rid of the pawns. Yeah. Once you capture that, you can take it. Let's clean this all up. Sure. Prevent the king from doing anything. Sure. Right. Okay. Let's feel like that could have been a faster checkmate, but let's continue with
Vulkan has an
this.
additional abstraction known as descriptor sets. Descriptor sets can be pretty confusing at first, since there are a few things going on at once, but I will do my best to untangle this concept. Think of a descriptor as like a pointer to a resource. A buffer descriptor, for example, would point to the global UBO buffer object we created in the previous tutorial, and an image descriptor could point to an image and a sampler. Unlike a conventional pointer, these descriptors also store some additional data, such as the size and offset for the buffer type, and an image's layout for an image. Now, to further complicate things, descriptors cannot be bound individually and must be grouped together into a set. This is mainly for performance reasons and is one of the advantages of Vulkan over older graphics APIs such as OpenGL, where each uniform needs
Can't bind descriptors directly either.
to be updated individually. For example, if we have a complicated shader that uses 3 different uniform buffers and 5 different textures, it'd be inefficient to bind each of these individually. Descriptors should be grouped into sets based on their binding frequency. For example, the projection and camera view matrix will likely be the same for every object rendered in the scene, so it would make sense to put the descriptors that point to the global UBO buffer that stores these objects into set numbered 0. If we also have a buffer containing all the light sources within the scene, this is also likely to be shared by all objects in the scene and could be also put into set 0 as well. Then all the resources that change per object could be grouped into set 1. This way, we only have to bind set 0 once, and it can be reused for every draw call in the frame. This improves the device's rendering performance because it won't constantly be swapping out resources. It is common to see even more sets than just 2 being used. Binding textures for materials can be expensive, so it can be beneficial to have a descriptor set dedicated to binding image descriptors and then grouping object draw calls based on material usage. If you're targeting mobile, you need to use some conservative limits. The minimum spec of Vulkan guarantees only 4 max-bound descriptor sets. Before a pipeline is created, it needs to be told what descriptor sets to expect. This is done through the use of a descriptor set layout object. This is like providing the pipeline with a blueprint of how many descriptor sets to expect, as well as what descriptor types to expect within each set. So, for the previous example, the blueprint, aka the descriptor set layout, may look something like this, where we say there's going to be 3 sets, with the first set having a buffer descriptor that will point to a buffer that contains the camera and environment variables at binding 0. and at binding 1, a second buffer that points to the buffer of light sources. Then set 1 would be the blueprint saying to expect 5 image descriptors at bindings 0 to 4, and set 2 would just say to expect a single buffer descriptor at binding 0. So also note how each set has its own bindings, so you can reuse binding 0 for set 0, and binding 0 for set 1 is completely different. Okay, then after being created with these descriptor set layouts, the pipeline will then expect at runtime the descriptor sets to be bound into each of these slots before a draw command is called. Now,
This is going to be
as one
quite a
final step
long
of
one.
complexity, we cannot create descriptor sets directly. A descriptor set needs to be allocated from a descriptor pool object. This is also for performance reasons. Allocating memory can be expensive, so descriptor pool allows us to allocate a big chunk of memory at one time that can hold many different descriptor sets. Then we can assign the memory from the pool as descriptor sets become needed. Now, that was quite a lot, so let's go over a quick summary. And it may be worth watching this section again so that you really understand the purpose of each component and the relationships between them.
Let's see the comments. I was hunting info about your views and descriptors since I was trying to understand. Looking for more grounded, easy explanation on this topic. Watching this series as a TV show, just for the explanations. Last time I tried my hand at Vulkan, this is where I failed. So I'm glad you are covering this.
Descriptors point to a resource, such as a buffer or image, and contain some additional data specific to the resource type. Descriptors need to be grouped into sets before being bound, so in Vulkan you cannot bind an individual descriptor. A descriptor set layout is like a blueprint that is provided for pipeline
To group
additional data specific to the resource type. Descriptors need to be grouped into sets before being bound, so in Vulkan you cannot bind an individual descriptor. A descriptor set layout is like a blueprint that is provided for pipeline creation. This way the pipeline knows what to expect in terms of how many sets, what types of descriptors they contain, and at which binding. Before making a draw call, we need to bind each descriptor set to slot into the active pipeline. And finally, descriptor set objects can only be created by being allocated from a descriptor pool. Now, before starting with this tutorial, there's a small change to make to the buffer implementation file. In the map function, we want
bind descriptor sets before draw call.
and finally, layout is like a blueprint that is provided for pipeline creation. This way the pipeline knows what to expect in terms of how many sets, what types of descriptors they contain, and at which binding. Before making a draw call, we need to bind each descriptor set to slot into the active pipeline. And finally, descriptor set objects can only be created by being allocated from a descriptor pool. Now, before starting the map function, we want to remove this if statement that passes in the buffer size. If you completed tutorial 19 after October
Buffer. The buffer CPP. Controlling map. Okay.
the file I provided would already be updated with this change. We want to pass through the VK whole size value when specified, as this signals to the Vulkan driver that we want to use the whole memory range, and behind the scenes it may allocate a larger range than the actual buffer size, in order to be compatible with a specific GPU device in use. So we are going to start by coding an abstraction to make all of these objects for descriptors more convenient to create. I am going to group all of the descriptor-related abstractions into a single class called LVE descriptors.
Yeah, let's create the new file. New HTTP LV descriptors.
Paste bin links for the descriptor header and implementation files are provided in the description below. Start by copying the first class, LVE descriptor set layout, as well as the include statements into the descriptor's header file. Rename your device header, namespace, and class names to your project conventions. Also add a closing brace to complete the namespace block. Okay, let's go through this. The nested builder class.
Okay, he's just combined both of them into one. Now there's space. There's let's get the okay, the class is different. Okay, and let's make the CPP file. All the descriptors.
Class is just a convenience class for building the descriptor
Variables. Build a add binding. And unique pointer set layout. Um, As it keep coming to the side here. Unordered U and oh, right. This is one thing. Okay.
that blueprint object that the pipeline requires at creation. The add binding function appends to the map of bindings the information that Vulkan requires, saying what type of descriptor type to expect, such as a uniform buffer, storage buffer, an image buffer, etc. And then the shader stage flags tell Vulkan which shader stages will have access to this binding, so be it the vertex stage, fragment stage, or maybe both. Finally, there's a count. This is kind of confusing because so far, all the examples I've shown is that each binding has only one descriptor, but each binding can actually hold an array of descriptors of that type, which are then accessed in a shader by indexing into that array. For now though, we will stick with a default descriptor count of 1, but eventually we'll start using this feature. One last thing to note is how the builder class returns a reference to itself. This makes it easy to chain multiple of these add binding function calls together, and then to call the build function as a final step to create an instance of the descriptor set layout wrapper class. So use of the builder class is optional. Its main purpose is just to make constructing the unordered map of bindings easier. Alternatively, we can construct a descriptor set layout directly by passing in a list of bindings to its constructor. I also declare here a destructor which will clean up the VK descriptor set layout object this class is responsible for managing, and delete the copy constructors.
And this is the destructors.
In the paste bin, copy the descriptor pool class. This class also provides a nested builder class to make creating an instance of the pool object more straightforward. Again, by returning a reference to itself, each of these function calls can be
Can use the pool and then the right. Control C.
changed together. A descriptor pool needs to have declared ahead of time how many descriptors of each type to expect. For example, we could add a pool size of 100 uniform buffers and a pool size of 100 image samplers.
Descriptor tab, descriptor count. Yeah, welcome Rahul. Let's
The pool flags configure
continue
the
this. This seems to be the final major complicated ones. Let's see. Yeah, all the other tutorials are much shorter. Hopefully I can finish all of these by this weekend. And to edit a video about this on the weekend at least.
behavior of the pool object, and we'll cover these in more detail in a future tutorial. And max sets is just the total number of descriptors that can be allocated from this pool object. The descriptor
Mhm.
pool object is responsible for managing the VK
Here we go. The device descriptor pool. Mhm.
descriptor pool object, and it provides functionality for allocating and freeing descriptors from the pool, as well as the ability to reset the entire pool and all descriptors that have been allocated from it. The final class to copy over is the descriptors
Allocate descriptor.
that have been allocated from it. The final class to copy over is the descriptor writer class, the purpose of which is to make building the actual descriptor objects easier. So it is in charge of allocating
Let's hit enter. Let's format this a bit better.
descriptor set from the pool and writing the necessary information for each descriptor that the set contains. Note that the descriptor writer class has been marked as a friend of both the pool and set layout classes, meaning it will have access to the private member variables. Okay, now let's add the descriptors implementation file.
Let's copy paste the whole file. Right. So copy Control AC, Control V, Control S. Control S, add binder. This I think can all fit in one line. Yeah. That's I'll just keep it like this. Constant descriptor set. Let's do this. And just clean up any functions we can find. The device layout. Set enter. Okay. Let's go through all of this. This can be one line. Yeah, it fits. Plus say max full size. Delete. Let's do it this way. Yeah, should be fine. This can be one line. Hmm. Yeah, let's hit enter. Okay, that's fine. This can be one line. Load save. Okay. Layout is kind of done. Hmm. I will keep it. Let's make this a new line. Let's hit save.
Start by copying the first section for the descriptor set layout builder functions. Paste it into your codebase and add a closing brace to complete the namespace. So this is pretty straightforward. The add binding method checks to make sure a binding at the specified index hasn't already been added, and then configure the Vulkan struct with the descriptor's layout. Back in the paste bin, copy the next section for the descriptor set layout. The
Bindings.com bindings.
map of binding numbers to binding definitions is more useful for our purposes, but Vulkan for the descriptor set layout. The constructor takes the map of bindings. The map of binding numbers to binding definitions is more useful for our and then configures the Vulkan struct with the descriptor's layout. Back in the paste bin, copy the next section for the descriptor set layout. The constructor takes the map of bindings. The map of binding numbers to binding definitions is more useful for our purposes, but Vulkan only cares about the binding definitions.
Okay, binding definitions. This can be any of the autos. Specify. Control F auto. I got rid of all of them. Save.
The first thing we need to do is to create a vector of just the set layout bindings. Then we configure a Vulkan create info struct, as we've done many times throughout this tutorial series now, and finally call vk create descriptor set layout. Then we configure a Vulkan create info struct, as we've done many times
And create an info.
throughout this tutorial series now, and finally call vk create descriptor set layout to create the set layout and store it in the class's member variable. The destructor's only purpose is to clean up the descriptor set layout when it is no longer needed. Next, we have the descriptor
And destructors though. The descriptor set, this is descriptor pool. Pool builder. Right. Well, like, this could all be like different scripts. They don't all have to be lumped. together.
Like this is all pretty self-explanatory. One thing I'll point out here is that we are using implicit construction to add a vk descriptor pool size struct instance to the pool sizes vector. Then fetch the descriptor pool functions from the paste bin to construct this vector construction to add a vk thing. I'll point out descriptor pool builder. I feel like this is all pretty self-explanatory. One thing I'll point out here is that we are using implicit construction to add a vk descriptor pool size struct instance to the pool sizes vector. Then fetch the descriptor pool functions from the paste bin. The constructor and destructor are what you'd probably expect. We configure Vulkan create info struct with the passed in
Set pool size, set pool flags, set max sets, build. Pool size dot data, pool size dot size.
information, and then call a Vulkan create function. And the destructor cleans up the underlying Vulkan pool object. The allocate descriptor function will allocate a single descriptor set from the descriptor pool.
Let's continue. These are the descriptor pool.
In hindsight, this maybe should have been called allocate descriptor set to make it clear that we are allocating an entire set, not just a single descriptor. You can't allocate single descriptors. The entire set must be allocated at once. Note that we are required to provide a Vulkan descriptor set layout object. This is descriptors and of what type that the set of descriptors contains. Now, what would happen if we tried to allocate a descriptor from a pool that has no descriptors remaining?
Shift F6. Allocate descriptor set. Yeah, okay.
Well, the allocation will fail, and if your engine doesn't have some way to handle this, it will crash. A common solution to this is to create a pool manager abstraction. What this does is keep tracks of a list of pool objects rather than a single pool. If a pool becomes full, then a new pool can be created and added to the list. vkguide.dev has a very nice example of what I'd consider a more production-ready descriptor abstraction. His implementation has
vkguide.dev. Let me check this out. vkguide.dev. Building project. And grab CMake as its build. Press configure button. Here. Let's see this. Library tasks. Includes vendor, other JavaScript and stuff. Oh, what? This isn't the actual setup tutorial code. GitHub repo. Necklace. Doesn't seem to be that great.
As this pool manager functionality, as well as caching of descriptor set layouts
Let's
for
see.
improved performance. It's something I definitely recommend looking into at some point. For learning purposes, I think the simple abstractions provide.
Let's play a game of chess. I'm getting a bit bored. Let's play some simple. Let's kick the queen out. And bring this forward. Can block this. Let's get rid of that. Let's spin the knight. Let's go here. Let's attack this. Let's castle this way. Giving it up for free. Okay, let's grab the queen. So check. Get another queen. Nice. This one had 2 misses. Anyways, let's get
Provided here
back
are a
to
good place to start
this.
as you get comfortable with the concepts introduced in this video. Then, the free and reset functions wrap Vulkan commands to free a specified list of descriptors or to reset the entire.
Let's see. There's a lot of scrolling in this file. Okay, free descriptors here. I think this can all fit in one, right? Yeah, that's fine.
Finally, copy and paste the descriptor writer class. The write buffer function takes a binding number and a pointer to a buffer info object. It first
And descriptor writer 0.
checks to make sure that the binding number has been defined in the binding descriptions of the set layout. It also ensures that the descriptor count in the binding description
And this is just to check for the binding.
is in fact just 1. When we start working with arrays of descriptors, we will need to add another function to the descriptor writer class that takes a vector of buffer info objects instead. The function then configures a Vulkan object and adds it to the descriptor's array of writes to perform. The write image function is the same, except it takes a pointer to image info and sets the write.p image info field
Right buffer, right image. Okay, it's the same, but image info.
to use this value.
Yeah.
The build function then allocates a descriptor set from the provided descriptor pool
What happened to my screen? It just blacked out. Is my stream going fine?
This function
Let me just wait for this to load back up. It's glitched. Okay, the Twitch seems to be working. Let me check if the YouTube is working. If any of you can hear me, just type in the chat. Yes. Seems to be
sets the target
working.
destination set of all the descriptor set objects to write to the newly
OBS has just crashed for whatever reason. Let me create another. Okay. And bring this here. What's this? Okay, I'll leave it for now. If it's also working, that's good. Is it able to? It's not even getting the.
and finally calls the VK
Okay, started getting Microsoft Edge. Something has crashed in the background. I think wallpaper engine crashed. Hmm. And my entire background is gone. Let me try just restarting CLAN. Let load. Hmm. Yeah. Seems to be properly detected now. It's just that CLAN takes a while to load. Hopefully this isn't an issue because I spilled water on my computer earlier.
Descriptor set's write command to update the destination set with all the writes that have been recorded to the descriptor writes array.
Hmm. Okay, it's back. Let me check on Twitch. Let's see. Twitch has it loaded? Yeah. Okay. The OBS is still glitched out. But for now, this is fine. Let's continue.
Performs two actions. It allocates a descriptor set and stores the handle to the newly created descriptor into the set variable. It then updates the descriptors within the set by writing all the previously recorded write commands to the target set, updating the resources each descriptor points to, and the associated descriptor info, such as size and offset for buffer type descriptors, and image layout of image type descriptors. If you already have a descriptor set that has been created and only wish to update its descriptors, then you should just call the overwrite function directly. Okay, now it's time to use these classes to create descriptor sets and layouts. Head to your app header and include your descriptor.
First up, HTTP. Should include Internet plus. Let me close all the old things. Yeah. Okay, HTTP.
Then just above the game objects, I'm going to add a new unique pointer member variable with type descriptor pool called global pool. The way I plan to structure things is that any descriptors that
STD. Unique level descriptor pool global pool.
shared by multiple systems can use this global pool object. If the system's lifespan is temporary and allocates descriptors using this global pool.
Okay, order of declaration. Is it him? Order of declaration methods. Was it only work with today? Or not fixed? Let me say there's a plugin for this. That just has like a bigger variety perhaps to do To do status, doing, finish, SSS, important emergencies. To do highlighter, quick to do, see hint. Okay, cancel.
Make sure to free those descriptors within its Descriptor so that they are properly cleaned up and don't hang around past the existence of the system. If a system has descriptors that are only relevant to its own functionality, then the system could potentially create its own pool objects specific to its needs. Also note that the declaration order here matters. Member variables are initialized from top to bottom and cleaned up in the reverse order. We need to have the global pool variable declared after the device, because on closing, we want the pool to be destroyed before the device is. Alternatively, in the app destructor, you could set the global pool to equal null pointer. That way it'll be guaranteed to be destroyed before the device is, and the declaration order here wouldn't matter. Okay, next. In the app implementation, note that your code here may look a bit different to mine because I actually recorded this before I made the previous video that fixed.
First up, CPP. First up, run. Yeah.
In the app constructor, I'm going to initialize the global pool
Not doing it here anyway.
by using the Descriptor pool builder. I'll set the max sets equal to max frames in flight, because for now we only need the type uniform build. That's a 2, and that contains 2 uniform buffer descriptors. Now, for example,
Yeah, let's do global pool equal LV descriptor pool builder LV device dot set max sets LV structure max frames in flight add pool size vk descriptor uniform LV structure max frames in flight or build.
also add a second pool size 2, but with type storage buffer. Each descriptor set can be made up of any combination of
Storage buffer.
within the pool. So we could have one set with just a single uniform buffer descriptor, and the other set with a uniform buffer descriptor and both storage buffer descriptors. Or both sets could be the same, with one descriptor of each type. And there are many other possible valid combinations. But what we can't have is 2 sets each with 2 uniform buffer descriptors, since the pool only has 2 descriptors of that type to give out. And if the first set created already has the 2, then there are no more descriptors of that type remaining in the pool to give. We also can't have 3 sets like this, because even though the pool has enough descriptors to give out, we can create at most 2 descriptor sets, as that is what we specified as the max sets value for the pool. Okay, so get rid of the storage buffer, and now that we've made a pool object, next we need to create the set layout. Inside the run function, underneath UBO buffer.map, add a new local
I zoned out a bit.
at most,
Let's go back.
and with one type storage buffer within the pool. So we could have one set with just a single uniform buffer descriptor, and the other set with a uniform buffer descriptor and both storage buffer descriptors. Or both sets could be the same, with one descriptor of each type. And there are many other possible valid combinations. But what we can't have is 2 sets each with 2 uniform buffer descriptors, since the pool only has 2 descriptors of that type to give out. And if the first set created already has the 2, then there are no more descriptors of that type remaining in the pool to give. We also can't have 3 sets like this, because even though the pool has enough descriptors to give out, we can create at most 2 descriptor sets, as that is what we specified as the max sets value for the pool. Okay, so get rid of the storage buffer, and now that Next, we need to create the set layout. Inside the run function, underneath ubo buffer.map, add a new local variable with type auto global set layout equal to descriptor set layout.
Run auto global global set layout. Well, I'll be descriptor set layout builder, I guess. Yeah.
So our layout will have a binding at index 0 with type uniform buffer and will be used by the vertex shader. Then call
Vertex shader search. Okay.
build to create the descriptor set layout. So recall that we want to group descriptors into sets based on binding frequency. This global set will be the highest level set common to all of our
Yeah.
The way I'm organizing things here isn't final, and feel free to change it based on your plan.
Oh.
It might actually make more sense to have a single render system manage this. Might actually make more sense, and feel free to change it based on your plans for your engine. It might actually make more sense to have a single render system manage this. Kind of a master render system that has subsystems for performing certain rendering operations. But since we don't have that set up yet, I'm going to manage this global set layout within the app to demonstrate how we can then pass the layout down into child subsystems. Okay, now we have both pool and layout objects, and it's time to create our actual sets. I'm going to create a vector of VK descriptor set objects called global descriptor sets, with an initial size of max frames in flight, since we'll have
steady steady vector
set per frame.
steady vector VK descriptor VK descriptor VK descriptor set global descriptor sets LV swap chain max times and flat for and
Handles are initially null and do not have any memory allocated to them. We need to iterate over this vector, and then for each
auto buffer info
allocate some memory and write its buffer info. This is exactly what the descriptor render class was created for. So
okay, descriptor writer global set
in a
and
for loop, but
set
using an int
layout
index since we'll need that, iterate over global descriptor.
store global pool
We can get the buffer info with the correct size and offset
add buffer 0 buffer info
by using the descriptor info helper function on the buffer class.
build.
An LVE descriptor writer instance, passing in the global set layout and global pool as arguments. We need to use the dereference operator since these variables are unique pointers, and we want to access the contents in this case. Write the buffer info to binding.
My leg has gone a bit
Zero,
numb.
and then build and write the descriptor set, storing the Vulkan handle to the newly allocated descriptor set into the global descriptor sets array at index I. Now build and run to just check that things are still compiling info to binding 0, and then build and write the descriptor set, storing the Vulkan handle to the newly allocated descriptor set into the global descriptor sets array at index I. Now build and run to just check that things are still compiling correctly. Nothing should have changed, as we still need to tell our simple render systems pipeline about this new descriptor set layout. We'll also need to update.
Let's save. Let's run this. Okay, it's loaded. Okay. And that's our
Use the
Vulkan.
global UBO struct at binding 0. So let's do that. First though, we'll update the frame info struct to also include
Frame info. Okay. Select VK descriptor. Select from global
full descriptor
descriptor
set
set.
field with type VK descriptor set. Next, in the simple render system header, I'll add a VK descriptor set layout argument to its constructor.
Simple render system.
This value
Global set
is
layout.
into the create pipeline layout function to tell the pipeline object what the layout of descriptor sets will be before it is created. Now, in the
Pipeline layout here.
system's implementation, we can update the constructor
Okay. Create pipeline global set layout. Create pipeline layout. Yeah.
create pipeline layout functions with an additional argument. And in the constructor, pass the global set layout into the create pipeline layout function call. So it's by setting the set layout count and p set layout fields that we tell the pipeline about the descriptor set layouts. A pipeline can take a list of descriptor sets with the order of each set in the list being its set number.
Push function, push size. STD. Vector descriptor.
So the first set in the list is set 0, and the next set would be set 1.
Descriptor.
So on. Here we only have one set, so that's going to be at set 0. Even though we just have the one global set layout value for now, we'll create a local descriptor sets layout vector in anticipation for when we will have multiple sets. Then we can set the layout count to descriptor set layouts.size, and first cast it.
Startup. Past event. T. Descriptor layout dot size.
32 type, and the pset layouts field to
Descriptor set layouts data.
data. Now, it was in our first app that we defined the global UBO that will contain the projection and view matrices, so we no longer need to provide this in the simple push constant struct. So I'm going to rename the transform field to make it clear that from now on this will just contain the model.
Shift F6. Rename it to model matrix. Shift F6. Search and comments. Model matrix. Yeah, nice.
Matrix. Scroll down to the render game objects function, and we can update push.transform with the new variable. And we also no longer need to be
model matrix as
computing the projection view matrix here.
push not model matrix.
We now do that in the app implementation. As a last step, before we call a draw command, we need to bind the descriptor set to the pipeline. We do this using the VK
transaction doesn't get used. VK command bind descriptor sets payment for get buffer.
command bind descriptor sets function, passing in the command buffer
Dot command buffer
fix and pipeline layout. The next fields are the first set and descriptor set count. So this also relates back to
listing as its own individual lines. Number 0. Function has 8 parameters, which is called as 5.
when you bind descriptor sets, you can bind multiple sets at once, but you must always specify the starting set. Every set after the starting set must then be rebound. So if I have 3 descriptor sets, for example, and have already bound sets 1 and 2, if I wanted to bind set 0, I must also then rebind every set that comes after 0, so 1 and 2 again. That's why you want sets that are shared more frequently to occupy the earlier set numbers. So for now, we're just using set 0 and a count of 1. Then we specify the descriptor set being bound, and then 0 and a null pointer as the last 2 arguments. These last 2 fields are used for
0, 1, and frame info, 0, null pointer.
which I'll cover in a future tutorial. Note though how we bind the global descriptor set outside the for loop of game objects. We only need to bind it once, and then global UBO struct values can be used by all game objects without the need for rebinding. Okay, I know this has already been a long tutorial, but we are almost finished. This video took a lot of effort to make, so if you can hit that thumbs up button below the video, I actually would really appreciate it. Now open your vertex shader so we can define the global UBO struct and update our simple push constant data.
Okay, now we're going to shaders, word shader, flag shader. This will be model matrix now.
The transform field to make it clear that this is now just the model matrix.
Shift F6, model matrix. Shift F6, model matrix.
And then to declare a descriptor set uniform, we use layout with the arguments set equal to 0, binding equal to 0, followed by the
Layout set equals 0 on 0, binding on 0, uniform global description. So
type name for our struct. Inside we
I had a feeling it was the C of both.
match the definition in that class. So add map4 projection view matrix field and a vec3 direction
Projection view matrix, light direction matrix.
to light field. And then name the instance of the struct. I'll call it UBO for now. The set
Let's say direction to light. This will be called UBO.
must match what we used when setting up our descriptor set layout. Update the code in the main function to make use of
Let's see, where's the global UBO set? Frame info, no. Is it in the model? HPPP, Vortex window, no. Descriptors buffer. See, get buffer. Find usages. It's only buffer. Is it under that first app then? Yeah, okay. Projection view and light direction. Yeah.
UBO struct.
At least
So
I know
multiply the
it's
projection view matrix in
different.
the GL position calculation.
Casual position. Projection view matrix.
Don't forget that order for matrix multiplication.
And to push dot model matrix.
And then we can remove the hard-coded direction to the projection view matrix in the GL position calculation. And don't forget that order for matrix multiplication.
Normalize and
then we can remove the hard-coded direction to light value and instead use
UBO dot direction to light.
in the light intensity calculation. I'll copy my push constant struct definition to the fragment shader just to direction to light value and instead use the UBO's value in the light intensity calculation. I'll copy my push constant struct definition to the fragment shader just to keep them consistent with each other. Even
Let's copy paste it here. Paste.
using it here. Note that we don't have access to the uniform buffer object because when we first created the set layout, we made it available only to the vertex shader stage. Okay, almost finished. We just need to fix up the app implementation a bit. To the simple render system constructor, we need to pass in the global set layout, arrow get descriptor set layout to fetch the underlying
Simple render system. Let's go here. Yeah. Simple render system dot get global set layout dot get description set layout.
handle. And then in our frame info below, we need global descriptor set, arrow get descriptor set layout to fetch the underlying Vulkan handle. And then in our frame info below, we need to pass in the global descriptor set for the current frame. And that's it. Build
Pass it to the frame info.
Nothing on the surface should have appeared to change, but we are now actually using the data stored in the UBO buffer. You can test this by changing the light direction field that we hard-coded in the top of the app implementation. This is probably one of the harder aspects of Vulkan. Even though nothing has changed on the surface, the buffer and descriptor set abstractions have opened up a world of possibilities for future tutorials.
Let's play this. Simple shader bit. Line 26. Add a fill, and this would be the show. First app. Shift F6. Paste. And direction to left. Control C. Shift F6. Paste. Now let's try. Now search field and push. Oh, wow. Yeah. Let's see. Okay, it's compiling the shaders. Okay. As loaded, is all looking correct. Okay. Nice.
Pass in pretty much as many fields as you may want into the global UBO struct, such as multiple point lights and whatever else. One thing to keep in mind is just remember that we have the same alignment requirements as push constants. Also, one last thing you may have noticed is that I never cleaned up the global descriptor set objects, and this is because they'll be automatically destroyed for us when the
Okay, let's add the align as 16. Align is 16. Yes. That's for a space there.
global pool is destroyed. So in this case, it wasn't necessary. And that's it. Thank you so much for watching, and keep on coding. Cheers.
Okay. Finally done with that. We have 7 more tutorials. This 23rd one I don't think will really matter because we're already using CMain. So that will end up being 6 more videos. I think we can get it done by this week. I'll continue with like 2 a day. Let's run the game, make sure everything works. Okay. I shall end stream here. Then I'll save everything to GitHub. And hopefully Everything looks fine on YouTube and Twitch.